Algorithm analysis for performance optimization. In the world of algorithms and data structures, understanding performance is crucial. Whether you're optimizing code for speed or memory efficiency, mastering algorithm analysis provides the foundation for building efficient solutions. This guide dives deep into how we evaluate algorithms using time complexity, space complexity, and asymptotic notation. You'll discover practical techniques that every programmer should know when designing scalable systems. The importance of algorithm efficiency. An efficient algorithm can mean the difference between a system that handles millions of users smoothly and one that grinds to a halt under pressure. In high-performance computing environments, even small improvements in execution time add up dramatically over billions of operations. Consider a sorting algorithm used in an e-commerce platform's search feature. A naive implementation might work fine with small datasets but will fail spectacularly as user traffic increases. This highlights why analyzing algorithmic efficiency isn't just academic, it's essential for real-world applications. By focusing on efficiency early in development, developers avoid costly rework later. It enables better resource allocation decisions and helps build resilient software architectures capable of scaling gracefully. Understanding time complexity. Time complexity measures how runtime grows relative to input size. We express this relationship using big O notation, which abstracts away constant factors and focuses on growth rates. For example, an algorithm with O(n) time complexity will take roughly twice as long to process double-sized inputs. However, an O(2 to the power of n) algorithm would experience exponential slowdowns with increasing n values. O(1) constant time operation, unaffected by input size changes. O(log n) logarithmic time, common in binary search implementations. O(n) linear time, typical for simple iteration through arrays. O(n) log n efficient for many sorting algorithms. O(n) superscript 2 quadratic time, often seen in nested loops. O(2) exponential time, usually impractical beyond small inputs. Knowing these categories allows programmers to make informed choices during design phase rather than discovering bottlenecks after deployment. It's worth noting that while Big O gives us general trends, actual performance depends on hardware specifics and constants involved. Still, it remains our best tool for comparing different approaches at scale. Mastering space complexity. Space complexity evaluates how much memory an algorithm requires based on input size. While not always as critical as time complexity, excessive memory usage can lead to serious issues like out-of-memory errors. When developing for mobile devices or embedded systems where RAM is limited, careful consideration of space requirements becomes absolutely vital. Even cloud-based services benefit from optimized memory usage due to cost implications associated with storage resources. Let's examine some examples. A recursive Fibonacci function consumes stack space proportional to its depth. Bubble sort needs only constant extra space regardless of input size. Merge sort requires additional memory equal to half the dataset size. Choosing between in-place versus non-in-place algorithms often involves balancing trade-offs between time and space complexities depending on application constraints. Modern garbage-collected languages automatically manage memory allocations, but understanding your algorithm's footprint still matters greatly for predictable behavior and debugging purposes. Asymptotic notation explained. Big O notation forms part of a broader family called asymptotic notations used to describe algorithm performance characteristics mathematically. These include big omega, omega, big theta, theta, and little o notations. Big omega, omega, represents lower bounds, indicating minimum time required by an algorithm. For instance, omega n means the algorithm will perform at least linearly with respect to input size. Big theta, theta, signifies tight bounds, describing both upper and lower limits simultaneously. An algorithm with theta, n log n, has worst case and average case scenarios growing proportionally to n log n. Little o, denotes strict upper bounds excluding equality cases. If f n equals o g n, then g n eventually dominates f n as n approaches infinity. Selecting appropriate notation depends on what aspect you want to emphasize, whether you need guarantees, expected behaviors, or strict inequalities. These mathematical tools help formalize discussions around algorithm performance, making communication among engineers precise and unambiguous across projects. Evaluating real-world algorithms. While theoretical models provide useful frameworks, applying them effectively requires understanding real-world context. Let's analyze two commonly used algorithms with their respective complexities: quicksort, average case O, n log n, worst case O, n superscript 2. Its performance varies significantly based on pivot selection strategies and input distribution patterns. Binary search always runs in O log n time provided array remains sorted. This makes it ideal for lookups in databases, indexes, and other ordered collections. Examining such cases shows how theory translates into practice while also highlighting limitations inherent in any model. Engineers must balance theoretical ideals against empirical realities during implementation phases. Caching mechanisms further complicate analyses since they introduce temporal locality effects affecting perceived performance metrics differently depending upon access patterns. Profiling tools become invaluable here, allowing developers to measure actual runtimes rather than relying solely on abstracted estimates derived from big O expressions alone. Practical tips for better algorithm design. Creating efficient algorithms demands strategic thinking about problem structure itself. Here are several best practices that experienced developers employ regularly. Choose the right data structure first. Hash tables excel at fast lookups, whereas linked lists facilitate easy insertions/deletions without shifting elements. Prioritize divide and conquer approaches. Breaking problems down recursively often leads to elegant solutions with improved asymptotics compared to brute force methods. Use memoization wisely. Caching intermediate results can transform exponentially slow functions into polynomial time ones, though care must be taken regarding cache sizes and eviction policies. Optimize hotspots identified via profiling. Don't waste effort improving parts of code that contribute minimally to overall execution times unless forced by architectural constraints. Understand amortized costs. Some operations may appear expensive individually but spread their overhead evenly across multiple invocations, leading to effective constant-time performance overall. Troubleshooting common pitfalls. Even seasoned professionals occasionally fall prey to misconceptions about algorithm analysis. Recognizing these mistakes early prevents unnecessary optimization efforts focused on incorrect targets. Mistake number 1. Confusing time complexity with absolute speed measurements. Just because something has O, n, doesn't mean it's slower than another O, 1, solution. Constants matter significantly too. Mistake number 2. Overlooking hidden dependencies within recursive calls. The master theorem provides systematic ways to calculate complexities arising from recurrence relations. Mistake number 3. Neglecting I/O operations impact. Network latency or disk reads/writes frequently dominate total execution times despite having negligible computational footprints themselves. Mistake number 4. Assuming worst-case scenarios apply universally. Many algorithms have excellent average case performances that only degrade severely under rare pathological conditions. Being aware of these potential missteps ensures accurate assessments that reflect true system behaviors rather than purely theoretical abstractions detached from reality. Advanced techniques in algorithm analysis. Once foundational knowledge solidifies, exploring advanced methodologies opens new possibilities for deeper optimizations. One powerful technique involves amortized analysis, which looks at average case performance over sequences of operations instead of single isolated events. For example, consider dynamic arrays that resize themselves when full. Individual insertion operations sometimes require copying all elements to larger memory blocks but occur infrequently enough that overall cost averages out to O, 1. Another sophisticated approach utilizes probabilistic analysis to estimate expected running times considering various input distributions rather than assuming uniform randomness. Randomized algorithms leverage probability theory to achieve desirable properties like guaranteed correctness with high likelihood or optimal expected performance under certain assumptions about datasets. These advanced topics enable handling complex situations requiring nuanced trade-off evaluations between different performance dimensions simultaneously. They also play crucial roles in areas like cryptography, machine learning, and distributed computing where traditional deterministic models prove insufficient for capturing real-world variability accurately. Case studies and empirical evidence real-world benchmarks provide concrete evidence supporting theoretical claims made earlier. Consider Google's PageRank algorithm, whose original paper demonstrated superiority over alternative ranking schemes through extensive testing. Data from industry reports consistently show that switching from bubble sort to quicksort reduces processing times by orders of magnitude for medium-sized datasets while maintaining comparable simplicity levels. A study published in IEEE Transactions on Software Engineering found that implementing spatial partitioning reduced collision detection computations in video games by approximately 68% without sacrificing visual fidelity. Such empirical validations reinforce the importance of algorithm analysis as a discipline grounded in measurable outcomes rather than mere speculation. However, it's equally important to recognize that benchmarks vary widely depending on test environments, meaning direct comparisons between different platforms shouldn't be drawn lightly without controlled experiments. Tools and resources for effective analysis. Several specialized tools exist to aid in algorithm evaluation processes, ranging from automated profilers to visualization utilities helping understand complexity relationships visually. Visual Studio Profiler offers detailed breakdowns showing exactly where most CPU cycles get spent enabling targeted optimizations. Prof. Classic Unix Profiler providing call graph information along with timing data for each function invocation. JProfiler, Java-specific tool offering heap memory monitoring alongside traditional CPU profiling capabilities. Kernighan and Ritchie's book The Art of Computer Programming, comprehensive reference covering numerous classical algorithms together with rigorous analytical treatments. CLRS textbook, Introduction to Algorithms, widely regarded as definitive source material containing hundreds of exercises reinforcing key principles learned throughout course of study. Future trends in algorithm evaluation. Rapid advancements continue shaping landscape of algorithm analysis, bringing forth novel challenges and opportunities alike. Quantum computing promises revolutionary shifts impacting conventional notions surrounding time/space complexity entirely. With qubits potentially solving certain problems exponentially faster than classical counterparts, new paradigms will emerge requiring fresh perspectives on evaluating algorithmic efficiencies previously thought impossible. Machine learning techniques applied to algorithm discovery pose intriguing questions about automation possibilities within field itself. Could AI generate optimal solutions given particular constraint specifications? Distributed systems necessitate rethinking scalability considerations involving network latencies, fault tolerance aspects, and consensus protocols, adding layers of complexity absent in standalone executions. Keeping abreast of these developments ensures practitioners remain equipped to navigate evolving technological terrain while maintaining strong foundations rooted in core analytical skills developed today. Conclusion: effective algorithm analysis empowers developers to create robust, efficient software solutions capable of meeting modern demands. Understanding time and space complexities lays groundwork for smarter decision-making during design stages. Applying correct notations like big O, omega, and theta ensures clear communication about performance expectations among team members working collaboratively towards shared objectives. Combining theoretical knowledge with empirical validation provides balanced perspective necessary for successful implementation, avoiding pitfalls arising from either pure abstraction or blind empiricism alone. Remember that no silver bullet exists. Choosing optimal algorithms requires contextual awareness, weighing trade-offs carefully according to specific use cases before finalizing technical implementations.